All right, so just waiting for it to currently go live on YouTube. Hi, everyone. Oh, Carla, drop it into the chat if you want to. That way, John can see it as well. I'll let you guys chat. Oh, chat. There we go. Hi, everybody. Thank you for joining.
All right.
You
Oh,
can hear
video.
me fine, right? Okay,
Is
perfect.
everyone able to hear me?
I can hear you perfectly. Maybe it's just
Okay.
Hazel's connection. Okay, I'll get closer. I'll get closer to the line.
Okay. There are already two questions. Hi, Carla.
Well, while we wait for a few more people to trickle in, would love to see where you guys are watching from. Feel free to drop it in the chat. Hello, hello.
Hey, everyone. Yeah, let us know where you're joining from. I'm joining from Bangalore, India, and it's like 10:30 p.m. here, 10:33 p.m.
Do we have someone from Pakistan, Spain, Romania, Nigeria, Ukraine, Malaysia, India? Wow, all over the
Oh,
place. Canada. This is amazing. All right, I guess we can kick it off. So yes, welcome everybody. Appreciate alchemists who came. If you're not an alchemist, welcome to our workshop being thrown by one of our alchemists, he's Gyan. She has been with us for quite a few years, and I'm an admirer of her because she's a huge proponent for education. She's also one of the founding members of Phoenix Guild, and if you haven't checked it out, please do. I mentioned to the alchemist that if you take a screenshot of what you've learned during this session, tag Gyan and also alchemist underscore HQ on our Twitter, and also post it where I told you to, then I'll give you guys some. And so I'll let Gyan take it away from here. Would be great if you can just do an introduction for those who haven't met you and just quick a little.
sure. Thank you, Jackie. And thanks everyone for joining. I see that some of you are joining from a very later time zone, like it's 1 a.m. in Malaysia. So, yeah, thank you so much. I'm going to keep this a very introductory session. So, everyone who is completely new to zero knowledge proofs, I hope you will be able to learn something out of this session. It's not advanced, it doesn't go too deep into the tech side of things. However, if there is more interest, I can definitely do that as well. So let me share my screen and get started. I'll do a brief intro, and then we can just get started with the session. Okay, see. Okay, my screen is loading. Okay, perfect. So, yeah, hi everyone. As Jackie already gave my introduction, my name is Gyan Lakshmi. Everyone calls me Gyan. I'm based in Bangalore, India, and I'm one of the co-founders of the Phoenix Guild, which is a community dedicated to education, helping more underrepresented folks get into the Web3 space. I'm also a developer advocate with the Starknet Foundation, which is a layer two based on zero knowledge proofs. And today's session is going to be, I've titled it a little funky, which is zero greater than L1. But it's going to cover the basics of zero knowledge proofs and why a lot of layer twos, which are now built on the principle of zero knowledge proofs, why are they taking off? Why are they becoming popular? And what do they offer? Before we talk about L2s, in today's session, we will cover an introduction to zero knowledge proofs. What are they? How did they start? What is the landscape? And what are the use cases? So I've switched it up a little bit. I've covered a bit of the use case, which is the validity rollups before the landscape. And then I have a slide for the landscape, and then we'll have some time for Q&A as well. Like I said, this is a very beginner friendly beginner friendly sessions. And the only thing for you to be able to the best way for you to participate in this session is to ask a lot of questions. So I'll just keep seeing the chat and see if there are questions. I will try to take a pause and answer it then and there. We'll take a pause after certain sections so we can have some productive conversations. It's just a few of us, so we can definitely make it more close knit and more customized for the audience that is present here. Okay, so let's get started. First, I want to introduce as to what are zero knowledge proofs and what is the main principle behind them. So, the main principle behind zero knowledge proofs is zero knowledge. That is, when you're sharing information or when you are communicating between two parties, there is some sort of, let's say, essential information or some sort of secret that can be game changing information, and that information should not be leaked while this communication is happening between two parties. So when you're thinking of zero knowledge, you should always think of a communication system where there are two parties trying to communicate with each other. One party is trying to prove that a certain statement is true without revealing the information behind critical information behind that statement, and there is another party which is trying to invalidate this particular proof. And that's how zero knowledge proofs are created. That is, it allows a verifier, which is the receiving party, to verify or to reason that an information that they receive is actually true without knowing the critical components behind that information. So for example, you can say that, for a very layman example would be that you can prove that you made a pudding with apples without having to reveal how many apples you put in the recipe, because that can be a key to how that recipe is made. However, you can always prove that you made a pudding with apple by making the verifier taste, the apple pudding. And they may ask you, how do they verify whether your apple pudding has apple or not? They may ask you to slice it from the top, they may ask you to slice it from the bottom, they may ask you to slice it from elsewhere, from the middle, or whatever, right? So, verifier tries to invalidate the statement that you made, that is, this pudding has apple, and you are trying to prove that this pudding has apple without revealing the secret of your recipe. That is, how many apples did you actually put in this pudding, right? So this is a layman example of how zero knowledge proofs would work in the real life, but there is, of course, much more complexity to it in the computational ecosystem. So there is a lot of the zero knowledge proof narrative is becoming very, very popular, especially in the last couple of years. Last year, it picked up quite a bit. A lot of layer twos announced their release on testnet, etc. And and people started looking at this concept really just very closely in the last couple of years. But zero knowledge proofs and or the notion of zero knowledge has been there for a long, long time. It was first proposed in the 1980s by three MIT researchers, Shafi Goldwasser, Silvio Micali, and Charles Rakoff. And this paper was extremely theoretical about how zero knowledge proofs would work from a mathematical concept. But the use cases of this paper or the use cases of this concept we are seeing now excessively in the Web3 space, right? In the form of layer twos, validity rollups, and all that. And there are different types of proof systems. So early on, zero knowledge proofs started with interactive proof systems. That is, the researchers who were working on these problems, they started with something called an interactive proof system where there were two parties, which is the prover and a verifier. Both of them have to continuously interact with each other in order for the verifier to verify that the generated proof is correct. Now, obviously, this is not a scalable system because if you think of computers, right? When two computers are interacting with each other, they or two people who are sitting behind the computers are interacting with each other. Most times in today's world, people interact asynchronously, right? You send a message to someone, you don't expect them to be online and respond immediately, but they do respond once they see your message. This is asynchronous communication, right? And proof systems did not become interactive proof systems did not become popular because this required both the prover and the verifier to be present at the same time in order to verify that proof, right? So that's how non-interactive proof systems came into picture, and one of the algorithms of the non-interactive proof systems became very popular, called snark proofs. So I wrote this small thread which is about the basics of zero knowledge proof systems. I won't go through this, but I'll just post the link if it's interesting. Okay, Miguel, you lost the sound. Is there a problem with the sound? Is everything good? Are you able to hear me?
I think he said he's okay now, so all good.
Oh, okay, 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 perfect. Okay, okay, thanks. Okay, perfect. If I miss some information or you didn't hear, just let me know, and I can just repeat it. Okay. So coming back to the definition of what zero knowledge proofs are, they are simply put an encryption scheme where one party, which is the prover, can prove the truth of a specific information to another party known as the verifier. And this proving is happening without disclosing any additional information. So think of the apple pudding example, right? You are proving to a verifier that you put apples in your pudding without having to give the additional information of how many apples, which is probably, the secret sauce of your recipe, to the verifier. And the verifier's job is to try to do test cases on this proof to ensure that the proof is correct. And in a mathematical context, what happens is there is a proof, that is a mathematical proof, that is generated, and the verifier tries to run, like, stress test this proof to convince themselves with the highest probability that this proof is correct. So this is what zero knowledge proofs are. They are an encryption scheme where one party, the prover, can prove the truth of a specific information to another party, the verifier, without disclosing any additional information. So, what are the types of proofs? We have interactive proofs where the prover and the verifier are constantly interacting and performing some actions in order to ensure that the proof is valid. Whereas in a non interactive proof system, it does not require communication or constant interaction between the prover and the verifier. The prover can generate the proof and give it. The verifier can verify it at a later stage also. So these type of zero knowledge proofs require additional computers or softwares that need to be able to generate these kind of complex mathematical proofs. That's why it took a while for these non-interactive proofs to emerge. One of the most popular non-interactive proof algorithms is snark proofs. They are succinct non-interactive arguments of knowledge. We will see that in just a bit. Okay. So I have a very small video that I play in most of my intro talks. It's a very nice video, and I will share the link of the full video. But I'm just gonna play
If you're a business
the
owner,
beginning of it to give you an idea of what zero knowledge proofs are. I'm gonna skip all these ads. Yeah.
Professor of Computer Science at the UCLA Samueli School of Engineering verify that some statement is true, and yet reveal no additional information beyond the fact that the statement is true. Zero knowledge proofs are being used in blockchains and cryptocurrencies. So cryptographers are excited about zero knowledge because of its amazing mathematical properties, but also because of its incredible applicability to so many different scenarios. What's your favorite subject?
I'd say math. some of these small problems can actually be really big and complicated. It's like a puzzle.
I love math for the same reason. Today, I'm going to tell you about a thing called zero knowledge proof. So in the zero knowledge proof, there are two people. There's a prover and a verifier. And I want to prove that something is true to you. But the weird thing is, I want to prove to you that it's true without telling you any reasons why. I remember when I first heard about it, I was like, wait, what? How could that possibly be, right?
Yeah.
So what do you see in this photo?
A lot of penguins.
Yeah, hidden among all these penguins is a puffin. Do you want to try to look for it? Do you see where it is? I know where it is, but I don't want to tell you. Do you believe me? You're not sure to believe me, right?
Yeah.
But what if I could prove to you that I know where the puffin is without revealing to you where it is? Let me show you. I took that photo that we showed you and I put it behind this poster here. Why don't you go take a look through that hole?
I see the puffin.
So when you look at this board, we don't know where the photo was, right? Was the photo like with the corner here, in which case the puffin would be all the way at this side? Or was the photo with the corner here, in which case the puffin would be on the other side? So this is a really simple example of a zero knowledge proof. I convinced you that I knew where the puffin was, but you didn't learn anything else.
Why do you study zero knowledge proof?
When I first learned about them, I just thought they were so cool. But it turns out they're also really useful, not just for finding like puffins. If you just type in your password and a hacker hacks into the computer, they can just get your password, right?
Yeah.
What if instead we could somehow use a zero knowledge proof to log in? You would just be able to prove that, hey, I'm Chelsea, without revealing anything to them. If you could do that, then it would be amazing, right?
Yeah.
Because then even if the hacker hacked into the computer, he wouldn't learn anything because even the computer doesn't learn anything. So Chelsea, in your own words, what is a zero knowledge proof?
Zero knowledge proof is proof to a statement. You don't show them why or what. You just show them a tiny segment or just do some sort of weird magic trick. That's not really a magic trick. And they will be convinced and you didn't show them why or anything like that.
Yeah, so there are different levels of teaching in this. You have teens and then you have adults, etc., etc. But it's a very fun video, and I posted a link as well for those who are interested. But we are going to move on from this video. Let me just close this. Okay. So as you understood, like from the video, we can understand that zero knowledge proofs are a way to prove a statement without having to reveal essential information, right? So you, for example, Dr. Amit proved that there is a puffin in that image without having to exactly tell where the puffin is, right? Similarly, another great example from a computational perspective is you can prove to a computer that you own an account without having to type the password or have a password for that matter, because in that, if you have a password, then the computer actually can learn of your password and exploit. But in the case of zero knowledge, you are proving that you are a particular identity without having to even use that password mechanism at all. So the computer can't hack you because they don't even have that information to hack you, right, in the first place. So that's exactly how it works. And there are a lot of different use cases in this space, which we will slowly see. We'll see some of them which are relevant to the blockchain space, but even otherwise, from a mathematical perspective and from a computational perspective, there are a lot of different use cases of zero knowledge proofs themselves. I have another fun game, which I'm not going to go through because I have some more content to cover, but I can share the link to this later on, which tells you like it's a fun graph building game on zero knowledge proofs as well. Maybe I can come back to this after I hit the 30-minute mark just to see the sentiment and see if more people are interested in getting deeper into this. So, whenever you're thinking of zero knowledge proofs, we have every zero knowledge proof itself that you generate will have three properties. The first property is called completeness, that is, and this is from a prover side, that if a statement is true, that is, if the prover is constructing the proof for a true statement, then the verifier can certify the prover possesses the required input. So if the prover constructs a proof based on a false statement, then the verifier will never be able to certify that the prover possesses the required input, right? So that is completeness. You have to generate a complete proof. You can't generate a partial proof, right? Partial proofs can easily be broken because they don't have the complete truth. The second thing is soundness. The proof should be generated in such a manner that it should be sound, and the verifier cannot be convinced that the prover does not have the required input when they do not. So one, the completeness has to be it you cannot generate a proof for a half baked truth, as we call it. And the second is the way you generate the proof should be very sound. You can't just generate the proof by using a weak algorithm. So it will not be sound and it can be easily broken. Because remember, at the end of the day, the zero knowledge proof generation is just an encryption schema. So you have to make sure that you're using the right schemas, and such that when you're generating the proof, that the statement cannot be falsified. These two, completeness and soundness, they look, the description and the feel of it looks and sounds similar, but both of them have got to do with different components of the way you generate the proof. And the last but not the least, zero knowledge. So the verifier should never be able to get any additional information from your proof beyond the statement being true or false. Details of the information and personal data of other parties, they stay anonymous. And this is the zero knowledge component of your zero knowledge proofs. So every zero knowledge proof that you generate should possess these three properties of completeness, soundness, and zero knowledge. Okay, now we are going into the different types of proofs or algorithms that are there in the zero knowledge space. Are there any questions so far just on the basics of what are zero knowledge proofs? Okay. There don't seem to be any questions. Okay. Perfect. Okay, let's go. Let's continue. If there are any questions, please feel free to put them on the chat, and I'll continue with the types of algorithms. Okay, there is a Q&A section where a question popped up. Okay. Adil has a question, which is, does ZK proof serves as a bridge between Web 2 and Web 3? You can, I don't think that's exactly the purpose of ZK proofs, but you can use them as a bridge between Web 2 and Web 3, which is, when you're thinking of Web 2, there is a lot of data that is currently being stored in the Web 2 ecosystem, right? For example, we have machine learning models that are running day in and day out and collecting information about us, right? And they deduce certain preferences or certain data, or they deduce certain patterns based on the data that we provide. So, but we still need those patterns, right? Some way or the other. When we go for shopping on Amazon or any other website like that, we look for recommendations. Can we somehow use zero knowledge proofs to still continue getting these recommendations, but keep our personal data anonymous, right? So, this is the kind of things that we can think about when we are thinking of bridging the gap. Um, I wouldn't say yes, that 100% it does bridge the gap, but we can think of use cases and solutions that can help bridge this gap. All right. Okay. Another question, which is, how do ZK proof implementations improve blockchain layers? So currently, zero knowledge proofs are being extensively used in layer 2 solutions, which are using the ZK proof mechanism to reduce the cost of transaction by, instead of running the entire computation, you just need to generate a proof. So you will understand that a bit more when I will share an example of it in the upcoming slides regarding validity proofs. Then you will understand like how layer twos are helping improve the layer 1 compute, which is what the title of this webinar is. That is, how are we using zero knowledge proof systems to secure layer 1s, or to increase the performance or make them better. Okay. So, just to give you a quick context of what are the different terminologies that you will hear when you start exploring zero knowledge proofs, you will hear two terminologies. One is snarks and one is starks. Both of these are algorithms that are based on that use the zero knowledge proof principle. Snarks, the full form is succinct, non-interactive arguments of knowledge, and starks are scalable, transparent arguments of knowledge. Snarks came earlier than starks. Starks were relatively came later because the research, it's a slightly more complex technology, so the research in out of that algorithm took a while. And here are the major differences between these two. One is snarks require a trusted setup. What that means is, in order to generate a snark proof, you need to have a ceremony called a trusted setup ceremony, which is done by a group of people, and there is a key that will be generated in that ceremony. That key is required to generate the snark proof. Okay. Whereas starks, they don't require a trusted setup. They use collision resistant hashes, and they don't need this trusted setup ceremony to generate that key. You can just generate a Stark proof using the Stark algorithm. Snarks use elliptic curves, which is potentially vulnerable to quantum attacks. So, elliptic curves, elliptic curve cryptography can be broken when quantum computers come into picture. So, it's not quantum secure to use ECCs. However, Starks are post quantum secure because they use collision resistant hashes. So that's the main difference. And then you have different, you are generating a proof, right? That takes a bit of time. And then you're trying to verify the proof. That also takes some time. And then the proof size, what will be the size of the proof? So these are the largely the three parameters on which you determine what kind of algorithm to use. So you see snarks have a trusted setup. So they compromise a little bit on the decentralization part, but their proof size, proving time, and verification time is largely okay. Starks, because they're fairly new, their proof size is little larger, but a lot of this, this is a slightly old, actually, this is a very old slide. So I'm sure this has completely changed now. This slide is from 2022 when I gave my presentation at ETH Denver. So I think these figures may not be exactly correct, but it's roughly similar in comparison. And bullet proofs is another type of zero ZK proofs algorithm, and snarks and starks are way ahead of bullet proofs. So this also, I think, is a slightly old statistic, but this shows the algorithmic complexity of the prover, the verifier, the proof size, etc., etc. Okay, so there are a lot of interesting use cases in this space, and I'm going to tackle one of the most popular ones, which is validity rollups or layer twos, right? And before I get to that, okay, before I get to that, I see that there are some comments. Maybe if there are questions, I want to check it out. Okay. Okay, I see Daniel in the house. Okay, all right. Okay. There is a question. What are some chains using ZK that are no longer in testnet? I know there is Polygon ZK VM, but it's still testing and the fees seem high. So Starknet uses zero knowledge proofs, and it's already on mainnet. So you can definitely check that out. Scroll, I think, is going to come to mainnet. So is ZK Sync. You're right. Just about most of the chains are just going to launch their mainnet. So Manta, Alio, there are a lot of different chains that are using ZK proofs, but I think they are going to come to mainnet very soon. So most of them probably gonna come now. Starknet is already on mainnet, so you can definitely check it out. If you're a complete beginner, this content is extremely helpful because this is just super basic content that I put up. ZK Sync Scroll both are on mainnet, seems like. I don't know if they have too much activity going on though. But yeah, okay, perfect. Okay, okay. Sandesh responded saying ZK Sync and Scroll both are on mainnet. So I'm posting that here. I think we can open the DAP radar and also see. Let's see actually, why don't we see right away? Because we are going to roll ups anyway. Okay, let's see. I want to see the chains. Okay, so we can see Immutable X was using Stark X as a service, but I think they are releasing their own ZK based stuff now. Let's see who else. Optimism and L2, but it's an optimistic roll up, so we don't have to see about that. I don't know scale if it uses. This is ZK Sync era. Okay. Linea is a ZK roll up. Okay, that's all I seem to be able to find. Maybe scroll doesn't have too many dApps. There's also this chain category L2s. Okay, we should be very easily able to see here. ZK Sync era Linea uses ZK. Maybe there are scroll is also on mainnet, but it's probably not that popular. Okay, how are ZK rollups gonna help cutting the transaction cost? I will show that very shortly. That's gonna be my next set of slides. Okay, let's do that very quickly. So we have all those answers. Then we will take more questions. Okay, so you will be coming across a lot of ZK based programming languages, right? For example, Starknet uses a programming language Cairo. You would have come across this programming language called Noir that Aztec is released, and then you might have come across this other programming language for ZK circuits. It's called Circom, right? So, what is the use case of all? What is the convincing statement behind having these ZK based programming languages, right? And what do they do? So this 2 3 slides are very created in very contextual to Starknet because we use the programming language Cairo, but it is pretty much more or less the same with any other ZK based programming language when you're going to learn that, right? So, for example, think that you are a space exploration scientist, okay? And you have been given a problem statement that you have to launch a missile, right? Having a basically, a launch is a very critical mission, right? So you have to think about a lot of different parameters that go into this, which is how do you save fuel? What is the best launch window? What is the best trajectory, right? And then there are a lot of other mathematical nitty gritties that go into this. So what do? You collect all of this, you make all of these algorithms, and then you get a bunch of engineers to implement these algorithms in some general purpose programming language, for example, Rust, right? Now, when and there is a problem, right? Now, the problem is that you have this really huge, really big algorithm, and your country doesn't have the sufficient resources to run this algorithm. So the execution of this algorithm needs a supercomputer, and the supercomputer is available only with a rival country. Okay. Now let's say this is the problem statement. Now, what happens in a typical scenario that you have an agreement with the rival country that I want to use this supercomputer for a short period of time just to run this algorithm, okay? And then you have some terms and conditions, etc. You give them that algorithm, the supercomputer executes that algorithm, and then it gives you a result, right? Now, if the result is faulty or if there is something not right with it, then how do you know whether it was actually the supercomputer's fault, whether the supercomputer malfunctioned, or whether there was a rival spy agency that tried to sabotage your work? There is no way for you to verify, right? And of course, as per your agreement, you can always say that, oh, this result is not correct, but you will never, you may ask them to re-execute it, right? That's what happens. If we get the wrong result, we ask someone to, hey, can you please do it again and see whether it is correct? That's the first tendency, right? Can you please re-execute this? But re-execution takes time, right? So you may have to pay them more, and maybe your result comes back as wrong again. So there is no way for you to trust, right? You can't trust them. However, if you write your program in some type of provable programming language, right? What is a provable programming language? Which can help you generate proofs. So if you write your program in a provable programming language, for example, here is the logo for Cairo. So I've just put it here, but it pretty much applies to any other provable programming language that you work with. So you send this piece of code to your rival country, right? This rival country supercomputer will execute this piece of code, and then they will not just produce the result, but they will also produce a proof. This proof is a proof of how your algorithm was executed. And as a verifier, now you are the verifier, and the supercomputer is the prover. The prover is trying to prove what are they trying to prove? That they executed the exact algorithm that you gave them. Okay, so they generated a proof for it. Now, as a verifier, all you have to do is verify whether this proof was correct or not. And the amount of time that it takes to verify whether a proof is valid or not is much, much, much lesser than re-executing that entire piece of code. This is how you optimize on a lot of time, and you can create a trustless cooperation between two parties who don't trust each other. So basically, if the execution is intentionally or unintentionally modified, the proof will turn out to be invalid. And in this way, your regular computer, that is you who's a verifier, who's just verifying this proof on your small regular computer, is able to keep a supercomputer honest. You're able to keep a huge execution body honest without having to do too much effort. Because if they use a provable programming language, they can generate a proof of how this algorithm ran. Or they use in Cairo, in the Cairo VM, we use something called as traces. But basically, they are not just giving you a result, they are also giving you a proof of how this result was obtained. Imagine how this can be a huge game changer in the blockchain space, right? Now that you have this context, now I'll show you how L2s using zero knowledge proofs help cut down the time in layer ones like Ethereum, right? Now the Ethereum scaling problem, let's the L1 scaling problem, let's consider Ethereum here. I hope most of you are familiar with the Ethereum ecosystem. That what happens in Ethereum when there is a transaction, right? There is a state change that happens. So what is a state change? For example, when you're transferring some amount of money from one Ethereum wallet to another Ethereum wallet, you are in the first Ethereum wallet, suppose you're sending 5 Ether from wallet A to wallet B. The amount of balance in wallet A should reduce by 5, and the amount of balance in wallet B should increase by 5, right? This is a state change. There is a state change that's happening in both of these accounts. And this is what your blockchains are all about, right? They reflect the state change in a trustless manner in a shared ledger. So now, every time, and what is a block? A block contains different, a bunch of transactions. Each of these transactions reflect a state change. So when you're producing a block, there is a set of validators on Ethereum that are rerunning all of these computation, all of this execution to verify whether the state change is correct or not. That's the job of validators, right? And then based on your consensus protocol, you decide whether a particular block is acceptable or not. And if it is acceptable, it gets added onto the blockchain. So for example, when a block producer is producing a block, let's say that there is a state change that the new state is 42, right? So what happens that this, whatever is the execution that is part of the block, that same execution has to be replicated by all of the validators. That's why Ethereum sometimes gets congested, because when there are a lot of transactions coming together, all of these validators have to re-execute all of them. So it takes a long time for them to do it and for the blocks to get accepted. So if there are too many blocks, the time increases as well as the gas fee increases. Why does the fee increase? Because the validators will pick the transactions that have a higher fee to put in the block, right? So, and they will still have to run the execution. So that's why the chain becomes extremely congested when there are lots of transactions that are coming to Ethereum. So this is the L1 scaling problem. You're not able to scale up. You're not able to do too many transactions. When suddenly you have too many transactions, the price goes up, right? And to solve this problem is where you see validity rollups, L2s, which are using the principle of validity rollups, come into picture. So what happens if you have a ZK proof based L2, right? Like Starknet. So here you see that there is this box which is running the execution. If you remember the result plus proof. So you create a result, which is the state change, but you also generate a proof along with that. That here is how this state change was produced. Now the validators, instead of rerunning this entire execution again, have to just verify this proof. They don't have to rerun the execution. They just have to verify this, whether this proof is valid or not. And if the proof is valid, that means this execution was run correctly, the way it was supposed to run. Because if the execution is not run correctly, this proof will become invalid. So the amount of time that it takes for the validators to actually validate the proof is way, way lesser than the amount of time that it takes for them to re-execute the entire um, transaction set, right? And this is how you can see that the timing that is taken by L1 is very, very less, and hence it makes Ethereum scalable, right? And because the timing is less, you can do more transactions, you can do fast transactions, you can do in a short amount of time. So obviously the gas fees also remains very, very less. And you are doing the result generation and the proof creation on L2s. And L2 gas fees is very, very less because it's not the same as the validator system of Ethereum, right? So the L2 gas fees are like, you can see that the gas fee in L2 is in cents. It's 10 cents, 5 cents, right? 1 cent. It's as less as it can be, right? Because these are like off chain computations. All you have to do is generate a proof and submit it on chain. And this proof, if it is valid, then the block is accepted. If the proof is invalid, then the block is rejected. So the motto is execute once, verify everywhere. So you can see that the time difference over here, just for a little bit of context, that if you see this blue graph, which is like the number of transactions as it increases, the amount of time that it will take to validate those transactions will also increase, and eventually the network becoming congested. However, with L2s, you can see this kind of like a saturated graph, that is after a point in time, because the proof verification is takes such a small amount of time that you don't have to worry about the scalability anymore. So this is how L2s, which are using zero knowledge proofs, are trying to make Ethereum more and more scalable with the way they're using the rollups. So now, you might have heard about the terminology roll ups, right? So, how do they work? Now, how the roll ups work and what are validity roll ups is basically, you have a bunch of transactions that are rolled up together. Like when you have a file and you want to send that file over email, you will zip that file, right? so that it becomes easier to transfer it. Similar to that, you have a bunch of transactions which are rolled up, and then there is a proof that is generated for all of these transactions. So for all of these computation, a proof is generated, which is called as the validity proof. And this validity proof is submitted to Ethereum. Ethereum verifies this validity proof, and if the proof is valid, the block is accepted. Now, we have been using the terminology zero knowledge proof, ZK proofs for most of the webinar, but suddenly I started using the terminology validity proofs. It is because most of the L2s like Starknet, ZK Sync, Scroll, all of these, they are all public layer 2s, right? They are public permissionless blockchains. So because they are permissionless in nature, if you remember the three properties of zero knowledge proofs, which is soundness, completeness, and zero knowledge, the last part, which is zero knowledge, is not completely available in these permissionless, right? Information is not completely zero knowledge. You can still go to the explorer and see the transactions that you do on L2. So it's not completely zero knowledge. However, they are called validity proofs because you can check the validity of that computation or of that state change using the same zero knowledge proof algorithm. You just don't have the zero knowledge part of it. You still use the same mathematical principles, but the information is not zero knowledge. The information is not hidden. It is available for you to check. That's why you will hear the terminology validity proofs in L2 proofs that are using the principle of zero knowledge, but they are not totally zero knowledge. And this is another reason why you might hear a lot of different narratives coming up, like L3s, app chains, and all of that. So they are using these algorithms, the zero knowledge proof algorithms, on top of these L2s to add privacy to the transactions. For example, Tornado Cash, right? They directly use the snark proofs and they built a system such that you cannot trace who did what kind of transactions, right? So those kind of apps can be built on top of L2s. So you get scalability and privacy by using these zero knowledge proof algorithms. So this is one of the use cases. Please remember, validity rollups is one of the use cases. There are so many different use cases of zero knowledge proofs that you can do. But I chose to explain with validity rollups because this is one of the most popular use cases and one of the most relevant ones today in the scalability narrative. Okay, so there are a lot of research that is going on in this space. So I have some QR codes for research resources and educational resources. I think these are like a bunch of videos that I curated, and then a lot of research articles, videos, etc. So I'm sharing this. But let me first go to the questions. Seems like there are lots of questions, and I'm going to. Okay. Okay. So how are ZK rollups gonna help cutting the transaction cost? Is that clear that now we are going to do a lot of computation is done off chain. So you are not going to pay for all of the transactions on chain. You're only paying for the verification cost, which is much faster. So it is much lesser, right? So, okay. There is another question, which is you said that the verifier checks for validity. So is the tech to verify transactions open source so that chain is decentralized, or is it just Stark team checking for validity? No. So the okay. So the verifier is on Ethereum, and the Starknet actually just produces the proofs of the transactions. The verifier is on Ethereum. So that is the beauty of L2s, right? Even though you have L2s, why are we still sticking to the narrative of Ethereum? Is because we need Ethereum security and decentralization. So we need the verification to happen at Ethereum level. That's why the verifier is nothing but actually it's a solidity contract which is deployed on Ethereum, and this verifier checks whether the proof is valid or not. So the tech is to verify the transactions that are generated by any L2. So for example, if you have Starknet, in this Starknet generates Stark proofs. Similarly, if you have ZK Sync, they generate their own Stark, whatever they are using, proofs at ZK Sync level, and that is verified on Ethereum. Same with Scroll. So that's why these are all L2s for Ethereum. Is it not that the L2 validation is centralized? You are right. So right now, most of the L2s are centralized because L2s produce the block, right? So they use something called as sequencers. So this is again some common terminology that you will hear a lot: sequencer. So sequencers are the one that are currently used in all L2s. Most L2s, I don't know about all of them, but most L2s use sequencers, and sequencers are the one that are producing blocks in L2. So every L2 has a roadmap. Okay, again, most L2s have a roadmap to decentralize. So L2s also will have their own consensus protocol and their own way of creating blocks. But right now, there are sequencers that are running the L2 block production. So it is centralized. However, there are a lot of open source projects that are also being released, which are building their own sequencers. So you can also use those sequencers. So in a way, decentralization is always already happening, but it's not completely there, and it's not as powerful as L1s yet. So it is in process. Yeah, so the network fee is sometimes super bad. So yeah, so ZK rollups, why do they matter, right? That's a great question. Because we think that the Ethereum ecosystem is already, quite problematic, and there are not so many realistic solutions. But if you see the Ethereum roadmap, there are a ton of improvements, especially with proto-tank sharding and a lot of other cool EIPs that are coming into picture. And not just that, you see a lot of L2s coming on top of Ethereum, largely because of the ethos of Ethereum, right? And one is ethos, and second is the community. The Ethereum community is one of the largest and one of the biggest set of people or projects that are already dApps that are already deployed on Ethereum. So it's a huge community. It's a huge effort in terms of ethos, and the way people started it was one of the first ever chains to provide the ability to program, right? Of course, after Bitcoin started as a source of value, and now it also has programmable ability, but Ethereum started as one of the earliest chains, right? So a lot of people believe in the ecosystem. That's why a lot of L2s are there to strongly support uh, Ethereum, right? The narrative is that the verification happens on Ethereum. But if you think about it, L2s using zero knowledge proofs or ZK rollups are such a powerful narrative in any way that even if it's not Ethereum, any other chain, L1 chain for that matter, like Solana or anything like that, is also able to use these rollup features, right? Because it is a very generic technology. If you think about it, you're just taking the transactions, you're bundling them together, you're generating a proof, and you're making sure that this proof can be verified on another layer, right? You can verify it anywhere. It doesn't have to be Ethereum, by the way, right? It can be verified single-handedly. It can be verified by individuals as well. But a lot of narrative is towards Ethereum because it's a bigger ecosystem. And not just that, there are a lot of L1s that natively use zero knowledge proofs. So you have Mina protocol that uses ZK proofs just to generate new blocks. You have Alio that also uses ZK proofs right at the very underlying privacy level. So ZK rollups are a narrative that are supporting the Ethereum ecosystem, but it doesn't have to be necessarily that. You can pretty much build a ZK rollup for Solana or any other L1 as well. So yeah, that's that. What would happen if an L2 goes out of business? I don't know. Whatever happens to any other product like that, any business that goes out of business, it's just the community that is invested. I don't think they will benefit out of it, or it will just collapse. People will lose trust in the founders, etc., etc. But you have to understand that most of the popular L2s are all coming from founders that are very veteran founders in the Web3 space. Like at least for Starknet, I can vouch for it, because it founder of Starkware, which is the company, and then Starknet Foundation is where I work, which is a not for profit. Uh, it is by a researcher who came up with the Stark algorithms, right? So these people are not just here like in the space to just release a token, create FUD, or make money, right? They actually want to make this technology better. So most of the you see a lot of recognition for these because of the founders, because of the past work that they have done. They might have contributed strongly to the Ethereum community early on, like Scroll and all of that. I think the founders are very well invested in the Ethereum ecosystem. Taiko, which is a project from the Ethereum EFESP, not ESP, sorry, the PSE, the protocol, or privacy and scaling exploration community. So all of these people are very well known, have done a lot of work, have contributed a lot in the past to different ecosystems. So I don't think L2s will collapse anytime soon per se, but of course we can never say about anything unless we see the actual mass adoption happening. Okay, perfect. All right, oops, I have only 2 more minutes. So I want to quickly share that these are resources. Just I'm not sure if this QR code is valid. I'm so sorry, I didn't make the check in the last minute, but I think it should be. Some of these resources are pretty good. And in case also if it doesn't work, I will share more in the Discord channel for Alchemist, and perhaps on Twitter as well. And yeah, just a quick landscape. This is the last slide I kind of wanted to just quickly go over. That this was the layer 2 is what we spoke about largely, this whole thing. Scroll, immutable XZK sync, Starknet consensus, etc. But there is, like I said, there are a lot of other use cases as well in the blockchain space. Like I said, there are layer ones that are incorporating ZK proofs right from the start. You have Alio, Mina, closely work with both of these ecosystems, and then some others as well. And then privacy payment, Tornado Cash, I'm sure everyone would have heard, and Zcash, Monero, Railgun. So Manta Network, very recently they launched, I think Mainnet also. Somebody was asking about Mainnet projects. So some of these other use cases as well. Then DeFi, you have some good projects, a lot of DeFi projects coming up on layer 2s as well now. Identity based projects, you have Sysmo, Ident3 by Jordi, who's now leading the Polygon ZK EVM team. Then ZK Pass, they are also becoming slowly quite popular. I've seen them at an event or two, so definitely look them up. And then some interoperability systems like bridges. Can you have ZK based bridges between protocols? Very interesting. Succent is doing a lot of good work. I recently saw some of their tweets and stuff. So definitely check them out. And Electron Labs as well. Uh, some cool stuff happening here. So ZK bridges can be an interesting topic. And yeah, that's pretty much it. I have a slide for Q&A, and I had a slide for Q&A, but this seems like I missed that. But if you have any questions, feel free to ask me. And yeah, thank you everyone for yeah, spending 1 hour of your time with me, learning something new. And I hope if you have any questions, then you will ask me on Discord, Twitter, wherever you wanna. Yeah, okay. There is another question about Daniel. Okay. Okay. So there is a question that do you think the ongoing stock market crash will impact crypto big time if it ever happens? Honestly, I'm not the best person to ask this. I think that with this user transaction, however, most of these L2s, at least from what I know, have already raised funding, have significant amount of funds, etc. So I don't think they are worried about that. And the whole idea of having scalability is to increase the user traction and get more users to come and build on your product, to start using your product, so it becomes more and more seamless. So I think that's the goal of L2, especially with the Ethereum ecosystem. And then the other thing is also that in the Ethereum ecosystem, you can see that the roadmap looks pretty neat. Like there is a lot of cool stuff happening for scaling, etc. So it will improve. I think it's not just a problem with Ethereum, it's just a problem with almost every other chain as well. So we are getting there. We are trying to make everything around the dApps much better. Great UI UX experience, seamless onboarding experience, and being able to reach out to more and more non-native crypto people, so that they can be onboarded, figuring out real-time use cases that are actually solving problems. I think these are the other things that we should look at from just a holistic perspective. I think it's not just the chains, it's also the kind of problems that we are solving with Web3. If we hit just the right kind of problems, we will be able to see mass adoption, right? Because that's what happened in just the technology evolution also. Okay, perfect. All right, then thank you everyone for joining. And oops, sorry, my dog is getting restless. But yeah, but yeah, if you have any questions, feel free to drop them on Discord, or I'm also available on Twitter. This is my Twitter handle, and yep, let me know. And if you have any feedback as well for the session, do let me know. And if you want any advanced topics afterwards, this was just like very basics, like just touch the tip of the iceberg, but there's so much to learn in this space. So if you are interested, just like drop me a message. Maybe we can sync up, Jackie, and have something like for the next level as well.
Yeah, would love a technical one. This was amazing. Really appreciate your time. Yeah, and like I love the workshops that you do, and I'm sure that the alchemists also really appreciate it and your time. I'll be compiling a little tweet, just giving like a little summary and overview. And for those that want to learn more about Gyan, just visit her Twitter and also the Phoenix Guild. It's also posted on Twitter too, with like the workshop info. But for those who weren't able to attend, the video is being recorded. It will be up on our YouTube, or starting from today, like our future workshops will be as well. And then I'll also provide the recording on the Notion page, so all the alchemists like have everything in one place. But yeah, super excited for more workshops. Thank you so much again. Appreciate it.
Thanks, Jackie. Thanks for having me. Bye.